fairly often they're distributed all over the country. There are hours drive away from each other. In some locations, they are tucked into the city in kind of these dense, difficult locations to get to. In other locations, the substation itself is an understandable environment to put a robot.
Welcome to another episode of the Mapscaping Podcast. My name is Daniel, and this is a podcast for the Geospatial community. My guest on the show today is Scott Nowicki, and he is going to be telling us about his involvement in the Mars rover project and how he's using that technology today to build autonomous robots that he is using to monitor substations. I'll let Scott explain exactly what a substation is and why it might be important to monitor it using a robot during the actual interview. But right now you just need to know that there's a whole bunch of geospatial technology at play here. We need incredibly detailed maps for these robots to work or orientate themselves by, and they themselves are building extremely detailed change detection maps as they move around this built environment. But again, Scott will get into more details in the actual interview. So this podcast has been running for about a year now, and during that time I've been trying to get it out to as many people as possible. But it turns out the best way to grow a podcast is by word of mouth. So if this is something you are enjoying and would be happy sharing with somebody else who might enjoy it, please do so. I would really appreciate it. It would help grow the podcast, it would help grow the community, and I personally would be very, very grateful. And if you haven't subscribed to the podcast, consider doing so. It just ensures that you don't miss out on an episode. All these episodes will be delivered to your podcast app automatically. As always, you are more than welcome to reach out to me for whatever reason on social media. Just search for the Mapscaping Podcast or Mapscaping on whatever social media channel you're on. You can also find me on LinkedIn. If you have any questions, comments, or feedback on the podcast, I would love to hear it. Okay, let's get on with the interview. Welcome to the podcast, Scott. So you are a remote sensing expert and you're the lead R&D scientist for quantum geospatial, and you've also been involved in the Mars rover project. So that's a lot to unpack in itself, and I know we've got some pretty exciting topics to talk about later on the podcast, but let's start with your background. Let's give the listeners an idea of how you got involved in remote sensing and how and what that has to do with the Mars rover project.
To begin with, I went to grad school at Arizona State University, and there I wound up working on a number of different Mars missions. So it was officially a kind of a remote sensing program within the geology department. I'm actually a geologist, so I spent a lot of time outside with rocks and everything else. But I spent most of my grad school experience designing instruments and then installing those on either the Mars exploration rovers or on satellites that we sent to Mars, and then proceeded to use the data that came back from those instruments in order to do really analysis of the globe of Mars itself and trying to understand where the best landing sites are from a safety perspective as well as from a scientific perspective. So that experience of being the scientist that works with engineers and programmers and operations people in order to actually make really kind of to solve a scientific problem, that experience is really what led me to get further into terrestrial remote sensing. And right now I work for Spatial, and in the company I do a lot of those similar things where we have a problem that we need to face. We have a problem we need to deal with, whether it's failing infrastructure or environmental characteristics that are changing or invasive species that we're looking for. And my job is typically to spec out what sort of instrumentation is needed in order to create the data that we really want in order to solve the problem. So even though now I don't really spend that much time working on Mars, the methodology for doing science was exactly the same. On Mars, I worked with incredible engineers and all sorts of people all around the world and really learned how to do this analysis. And now I get to kind of spin it off and do it on a smaller scale in quantum.
So let's talk a little bit about the smaller scale analysis that you're doing today, and can you help the listeners understand how you're coupling robotics with facilities management? So what is the link there, and what does this have to do with remote sensing geospatial?
So, really, the problems that I'm attempting to solve are those in determining the characteristics of a material from a distance. So, the remote sensing perspective of just making measurements without actually being in contact with it applies whether you're 300 kilometers above the surface or whether you're just like 20 meters away from an object on the ground. So the tools I'm really using are classic remote sensing, spectroscopy, and thermography, just using the right sensors in order to make the right observations of are things too hot or too cold? Are they rusty? Are they out of spec in one way or another? And it's what's funny is those exact same observations are the ones we were making on Mars, where we're using and the instruments that I worked on were thermal, infrared, either multispectral or hyperspectral instruments. The things we were looking for was the mineral hematite on the surface of Mars, which is actually just rust. And we were looking for the heat signature differences between like rocks and dust. And so, using those almost the exact same observations that we used on Mars, I'm using in a substation environment. So, from this kind of rover perspective, this robotic remote sensing tool, I'm able to look out and say, are there features that are out of spec from being too hot, too cold, deformed, or spectrally significant in some way? And even though it sounds very different, a substation is very different from Mars or even most natural environments. They're all the same kind of quantitative remote sensing tools, whether it's a thermal camera, a spectral camera, a laser system, a LiDAR system. They're all kind of the same things that we would fly on a drone or potentially fly on a plane in order to make these kinds of assessments of a facility.
Okay, so we've got robots moving around, and of course, I'm oversimplifying things here, but we've got robots moving around some kind of facility, taking measurements using different instruments, and I guess the instrumentation depends on the measurements we're interested in taking and monitoring. And so, what are we doing? Well, tell me a bit more about this facility, this substation. Is it inside? Is it outside? And why can't humans do this?
A substation, and all the rovers that I have are in substations. So we built 6 of them that are down in Texas. We built another 4 that are in Florida. And an electrical substation is really a switching station between, typically it's between transmission lines, these high voltage power lines, and the local distribution lines. So a substation is a relatively small area with lots of electrical buswork in there, switches, voltage regulators. It is kind of like the infrastructure needed in order to maintain this connection between transmission and distribution. And then there are just distribution substations, which are just places where there are switches coming in from kind of these lower voltage lines into the local houses and businesses. Kind of the purpose of the substation is to be able to convert energy from kind of one form to another and then distribute it locally. Within those operations, there are a bunch of moving parts. And these moving parts could easily have been installed 50 years ago and have been out in the rain and the snow and the hot and the cold. So, what we're doing is actually putting a rover into these substations in order to look at either degradation over time or small scale changes, or in some cases, large scale changes. That if someone were sitting there in a chair in the substation 24 hours a day, then yeah, they'd probably notice most of these things going on. But the whole idea is that really you can't have somebody sitting there watching it all the time. So that's why we try to automate this with a robot. And so if the robot is sitting in the substation, it can use all of these different tools in order to monitor what's going on, whether there are birds or snakes or iguanas entering a substation and potentially causing an outage, whether trees are growing over the fence line and dropping limbs into the substation, or whether components are just wearing out over time from getting too hot, getting too cold, or getting too rusty or getting too corroded, that they could potentially cause a failure. So the robot itself is, like I said, it's this remote sensing toolkit, but it's really a four-wheeled vehicle that is able to move around the substation totally on its own. It has a whole bunch of different sensors on it that allow it to be as autonomous as we can possibly make it. It can move on its own. It can take pictures on its own. It collects all of this data that we're really interested in seeing in order to say what are the changes occurring to the substation on a, sometimes it's minute by minute basis, sometimes it's per month, the kind of the scale of changes that we're looking for.
Why is a robot a good choice for this problem? Why do we need robots, and why is this not a computer vision problem? So immediately in my mind, I think, okay, we could install a whole bunch of cameras and different sensors, different places, pointing at known objects, so we know where the camera is, we know what's in front of it, we know the distance to it, and therefore we could make measurements on a regular basis in that way. Why is a rover a good tool for the job here instead of a solution like I was just talking about?
So if we could put hundreds of cameras into a substation and each of them providing all of the data sets that we need, then it would be great. We could totally map out an entire substation and monitor it on a minute by minute basis. The problem is that would actually be both expensive and really hard to maintain. So the idea behind a rover is that a robot that can run the substation is able to see everything as long as you're able to move it to that spot, and so it can get a good view of these kind of small scale features or even large scale features. But a robot is way more flexible than that system. If you set up your set of cameras so that you think you're observing the entire substation and you miss something, it's out of view or it's blocked by something in the way, then you won't be able to get that observation. The rovers, although, I mean, they are complex machines that we're putting into these substations, they're very flexible in terms of a changing environment. So if we're looking for an intruder, most of the time they can certainly do that. But then if you want to switch modes and be able to look at the conditions of the bolts on the buswork, right? It's like these really small scale features. Then you can easily shift between large scale monitoring of the substation versus kind of getting in and seeing really fine scale details that could potentially be causing a problem. Now, that's not to say that there isn't computer vision involved. So these cameras, even though it's only a couple of cameras on the rover, we're using those same tools in order to build a model of change that's going on in the substation. So even though it is a robot and it's going out and it's making individual observations that we kind of programmed into it, it is still feeding this data back to a server that we can use all of the computer vision tools we can throw at it in order to use this information.
Okay, so I can see a couple of things here. I can see, or I imagine anyway, and correct me if I'm wrong, please, that this robot needs a pretty accurate map of the substation in order to move around, in order to make decisions. So that's the first thing. And then I'm imagining that every feature in the substation needs to be matched as well. Because I'm thinking that if we're doing change detection, we want to be able to monitor that over time. And so we need to know that those observations are being made on the same features the whole time. So we build up a map of the substation each time we drive around, perhaps with the robot, and then we look for change over time in that map. Is that kind of what's happening?
Absolutely. We've got to start from this map view of the substation. So before we install a rover, we'll fly a drone and create a incredibly high resolution, really ortho image of the entire substation. So that gives us this kind of bird's eye view. Once we've got that map in place, then the rover itself is able to go out and, like you said, continue to map that three-dimensional landscape. And once we've mapped it out once, We kind of incorporate that into our model. And then the next time we go out and we rove, we can start to look at changes to that three-dimensional map.
Okay, so looking at changes to the three-dimensional map, obviously that this is a big part of solving the problem of you finding out if things are the way they should be, if things are to spec, I think is the words you used before. So I guess that means that for the model, we also need to know what spec is for all the different pieces in this model of the world that we're building.
Right. That's kind of where we started this whole process. Could potentially say you could start with a CAD model of a substation, say here are all the different features, and actually build them out in your model and be able to say you know here's the range of conditions under which it should be normally operating. But the reality is we don't know what those conditions really are and what those specs are. So if we were to say, let's have this entire substation, and if anything is 20 degrees hotter than the things around it, we'll call it too hot. But the reality is that that happens all the time because the sun is hitting different surfaces and it's heating up some things, and others are being cooled off by conduction or through radiation. So what we really need to do is generate those conditions, the normal operating curves of pretty much everything in the substation. So we go out, and even though we start with a map, we then have to build a range of conditions under which we think that things will normally operate. So if we're going to look at kind of the physical properties of a substation, even within that, conductors are moving a little bit. Some features are moving around. Certainly, the trees are potentially growing over the fence line, and all of those things move on the order of could be centimeters, could be tens of centimeters, could be millimeters, and just in terms of physical movement, we can't a priori determine kind of that range for each component in that substation. So we needed to go out and map it not just once, but tens of times, hundreds of times in order to say, oh, here's the normal range of variation that we'll see in terms of temperature, location, deformation, and these kind of other corrosion or reflectivity conditions. And it's only once we know what's the range in a given day or a month or a year that we can say, here's something that really is out of spec to the point that we need to deal with it.
Yeah, that sounds like a long-term process when you put it like that, taking into consideration all those variables and then the different times of year, the different times of day, what's the temperature like, what's the season like, has a storm just been through, something like that. That must be a massive data set to build up.
It is, but really quickly, the important things kind of rise to the top. When you start shaking things around, you'll see, there is a wide range of variability that if you tried to be as detailed as you could, you'd see kind of the small scale change, and you'd say that's normal. But the reality is that you only want to send a person into a substation to go fix some component when it's really bad, right? And so what we're doing is kind of starting from using the human brain, and we look at these conditions in the substation, and really a hurricane or a big storm that starts throwing debris around and really messing with the substation, that becomes so much more important than even these small scale thermal changes that we're able to see trending over time. So like there certainly is a hierarchy of change that we're seeing that makes it very apparent as to the first of all the value of having a robot in a substation, but then to like really determine what are the most important things that we care about when change is occurring in all these different dimensions all the time.
So one of the things I was thinking about there is that we're building these really intense and accurate models over a long period of time. Can I do this one for one substation and then transfer that knowledge to the next substation, or do I start from scratch each time?
No, there's a decent amount of overlap that we've been seeing, but there are very different substations. So we've got some robots in very urban locations in these pretty small places. The comparison of multiple urban distribution substations they are pretty similar. So we could see those changes and really apply them locally fairly easily. But let's say that's in Florida, and we've got a substation in some other location out in the desert, and it's completely different in terms of certainly the range of changes that we're seeing, but even the substations can be drastically different. Whether there's really kind of like the local environment really matters, how much weeds or trees on the surrounding, trees around the fence in a warm, humid place, then vegetation is absolutely fundamental to things going on in a substation. And in more arid locations, it really doesn't matter at all. So there are kind of they're pretty logical when you start thinking about it. Like, what is this? How big is the station? Kind of what are the different components that are in there? You can really kind of figure out what is different between these stations. But in terms of what is a real hazard, they're very, very different depending on environment and application.
Just to summarize here quickly, so we've got these land-based robots moving around substations, taking a whole bunch of measurements as they move around on set paths, I'm assuming. They've got very accurate maps of the substation at the start, and then they continue to build and create their own maps as they move around based on these different measurements. And so I guess at some stage these robots will be making decisions based on that sort of the normal distribution of change that they see. And when something comes outside that normal distribution, some sort of alert is generated. What happens to that alert? Is this all monitored in a GIS somewhere or some other kind of system?
Yeah, there's a couple of different levels of kind of analysis and then a result that comes out of it. So to start with, yeah, it's exactly as you described it. These rovers are going out on a daily or a weekly basis, doing a scan, which means LiDAR, thermal, multispectral, and visible imagery. And what we've really been doing over the past year or two is taking that step of like turning raw data into the right information in order to build these good maps of change. And that's great. Been kind of bracketing the range of temperatures and the range of conditions that we know that are safe or unsafe. But right, that next step of being able to tell someone to do something about it is the big step. And at the moment, we are still in the phase where we're collecting this data, we're generating our model of change, and then we're creating these exceptions. So it's either individual components are out of spec for one reason or another. So we are still at the point where we'll actually send those exceptions and all of the conditions to someone who actually works in the substation, and they'll decide what to do about it. So rather than say you need to, the robot is not getting to the point where it's able to say you need to change out this component, because we don't actually know if we need to change out a component or actually do some sort of physical change in the substation. So we're saying something is out of spec and delivering that information to someone who normally does an inspection, and they decide whether or not to do something about it. And the idea is if we do enough of these, we find enough of these exceptions to the conditions, that over time we'll build up a library of options that are relatively straightforward. That, well, if it's a tree branch has fallen into the substation, that's a pretty obvious solution that we could both identify the tree branch and identify the right action to take. But if a component is too hot, out of spec, we're not quite at the point where we can say, oh, we need to replace this component. We need to actually give it to a human that will decide whether or not that something needs to be done about it.
So I can definitely see the value of robots moving around substations. You know, they sound like dangerous places to work, and they're well mapped, and we have an accurate understanding of where things are in the substation, and perhaps not so many moving parts. How would this work in a more urban environment? So I think the holy grail for this kind of thing is having robots move around the world and do facilities management jobs all over the place, right? So moving around different areas, different environments. What needs to happen before we can move a robot from a substation environment, a known controlled environment, to a more urban environment where they need to make a lot more decisions for themselves? Is that where this is heading?
I think so. The highest value that we see right now are in these substations because fairly often they're distributed all over the country. There are hours drive away from each other. In some locations, they are tucked into the city in kind of these dense, difficult locations to get to. In other locations, the substation itself is an understandable environment to put a robot. There's value there that is specifically oriented towards having more eyes on the, in this case it's robotic eyes, but more eyes on the substation components, making sure that something doesn't go wrong, because when something goes wrong, it means the power goes out for somebody, whether it's a bunch of people in a neighborhood or an industrial client. There's a direct correlation between kind of component failure and certainly revenue loss, but along with that, power loss. So to take the next step and say we're going to use it in all sorts of in different facilities around the world, there needs to be kind of a well-defined, first of all, human infrastructure part of that. Are people currently inspecting and repairing parts in a facility, and what is the workflow that is kind of controlling that? And as soon as you're able to say, here are the things that a person normally does, and here are the kind of the conditions and the actions that are resulting from that, then it's actually relatively easy to put a robot in that space. As long as they can make observations that are similar to what the kind of human inspector normally does. So we've spec'd out a few different facilities and projects. Certainly offshore oil and gas pumping stations, things like that are ideal for robots, because you again, you don't want a human hanging out there all the time to do these relatively simple inspections, but it is a well-constrained environment that you could easily build a program for a robot to kind of monitor what's going on inside there.
I can definitely see some challenges around just letting robots go into very uncontrolled environments. Right now, we're talking about substations where we have a lot of control. They're known areas, and we have detailed maps of them. But yeah, I can see it's going to be it sounds like it's going to be a long time, I should say, before we just sort of release them into urban environments and say, go map, make maps of change and report back if you see anything that's out of spec. That sounds like a difficult task. So you mentioned that before you put a robot into the situation, you fly a drone over and you make very detailed maps of the area where the robot's going to be moving around. How much data do you need of the actual substation before you can start using robots in it? Can you just move into a completely unknown area and map it yourself? Or do you need some initial data input from somewhere else?
We certainly need a good map of the station that we're going to, or the facility that we're going to be operating in, because we're giving really the robot full autonomy in order to navigate without running into anything, to be able to go from waypoint to waypoint and like make the right observations that we want in order to monitor change. But that's all relatively easy to do. So that's one of the things that Quantum does on a regular basis. We fly LiDAR over power lines and substations, and then we build CAD models of these. But there's a human involved in that process. We got a nice three-dimensional point cloud that is highly accurate, but then the human has to go in and really draw these boxes around these features and be able to classify an entire substation. So we can pretty much go into a new environment, and as long as we know in general what is there, then we could map it out with certainly the LiDAR and the imagery that is on the robot itself. But that bird's eye perspective, this high resolution ortho image, is incredibly useful for just determining whether or not we can actually navigate within that environment. So the robot, it has object detection, it has kind of collision avoidance, it has all of these tools on there to be able to navigate through the human environment, whether it's, could even be an office space that we could easily kind of rove around. But in order to really understand what you're doing in those facilities, you need to be able to turn that raw imagery into an understanding of the significance in terms of what's actually happening within the substation, or what's actually happening within the facility that you're operating in.
I think what you're getting at there is like some sort of context. So it's one thing to know what the physical shape looks like. It's a whole nother thing to have some sort of context. This is an important piece of equipment over here. This can move. This is made out of metal. That kind of thing. Is that correct?
Yeah, and those kinds of things are sometimes easy to do with people on the ground looking at whatever visible imagery of that feature and being able to kind of draw a box around it, or using machine learning algorithms to be able to say, here, identify an object and be able to assign characteristics to it: size, shape, location, function. But they're relatively labor intensive. It takes a little while in order to actually build out a full model of what you're attempting to inspect, or what you're really just attempting to navigate through, as opposed to comparing it to like operating outside in a natural environment where you can build this three-dimensional model of everything that's in front of you. And really, you can't really assign that much context to rock, soil, tree, shrub, like all of these kind of natural features you can have a map of it and then try to navigate through it. But to actually assign significance to all these features and really kind of turn a point cloud into a set of features is pretty difficult. It takes a while to understand what's actually going on in an environment.
Like I alluded to before, I'd like to sort of move off now and talk a little bit about the future. And my first question is, will this always be a spatial problem? Will there always be a spatial element to solving this kind of problem, to looking to making change detection maps in situations like you're experiencing in a substation or in general facilities management?
I certainly think so. That is the approach we've been taking up until now. And by we, I mean like the large kind of inspection and geospatial industry. We really like robots, whether they're flying drones or whether they're on the ground robots, because you're able to navigate in this three-dimensional space. Unless we go back to that idea of you install just an incredible number of cameras that are able to cover an area, the idea of being able to not only change your perspective by changing your position, but actually changing the scale of the observations that you make by being able to move around. In things like substations, it's pretty straightforward. You can only go so far as the fence line, but in looking at, let's say, the power network itself, you've got transmission lines and distribution lines and substations and power generation. And the reality is that at some point, we're going to move to drones or robots or mobile mapping being able to observe the entire network. And if there's a problem, like a hurricane slams in Florida and destroys a bunch of the infrastructure, then you can actually have this scalable response if you're using these automated mobile networks. Then you can say, I'll start with some small area where I know that there's a problem, and then expand at who knows how many different orders of magnitude in order to encompass all of the problems that are potentially affecting the network. And I think the further we go to understanding systematic changes and trying to manage these large scale, especially infrastructure systems, then we're really going to have to scale in terms of kind of spatial and temporal scales, and really collecting the information that is required in order to solve the problem today, or whatever the problem is occurring on the ground right now.
Scott, I really want to thank you for taking the time to talk to us today about the problems you're solving, how you're solving them, and what the future of this technology might look like. It's been fascinating. Just before I let you go, can you let the listeners know where they can go to learn more about your work, or perhaps contact you?
Sure. So we've got a decent amount of information on the Quantum Spatial website. That's quantumspatial.com. Or you can visit my LinkedIn page.
Scott, thank you very much. Much appreciated.
Thank you very much.
And that's it for another episode of the Mapscaping Podcast. My name is Daniel. It's been a pleasure being your host again this week. Thank you so much for taking the time to tune in. It's much appreciated. And as always, you are more than welcome to reach out to me on social media. Just search for the Mapscaping Podcast and you'll find a way of contacting me. I'm sure of that. There's not too many podcasts out there called the Mapscaping Podcast. You're also more than welcome to connect with me on LinkedIn. That would be much appreciated. Any feedback, questions, comments on the podcast, things I can do better, things I can improve on, topics you would like me to cover, please let me know. I would really appreciate it and I would love to hear from you. Thanks again. We'll talk next week. Bye.